Okay, an introduction to a very exciting part of maths and optimisation. And we've done some work previously with derivatives, stationary points, maxima and minima, greatest and least values. And we're going to combine all that with an understanding of how functions behave, curve sketching, key points, all that together to do what's called optimisation, which can make the most or the least out of something depending which one is desirable. So let's look at some tips first. So make sure you copy down the important parts of the following in your notes. So be sure to summarise the essential parts out of this. So solving optimisation problems on an interval, which means there might be a restricted domain, and usually with resources or given quantities or lengths and so on, there are restrictions which creates an interval. Okay, so there usually is a restriction. After all, this is often about the real world. First point is just general problem solving. You need to be able to clarify the situation. So what do you know? What have you got to find? If you don't have some things you need to know, how can you get hold of them? So that's basically a clarifying of the problem. So very important with any problem solving. And what we can do then is, if possible, make a diagram, often very helpful, and label it. What's varying in this? Understanding the variable is part of clarifying, in fact. So, and variables will be related to the unknowns. And even if you usually can come up with a diagram, if that's not possible, you can still identify variables and represent them with appropriate symbols. So list all known facts and relationships once you've got these symbols and variables. So that's what you know, and then determine what you don't know and what you've got to do. So determine the quantity that has to be, is got to be maximized or minimized, and then express it as a function of the other variables. There'll be other things there that vary. So you need basically a independent and a dependent variable. What depends on what? Okay, so what is the independent and what is the dependent variable or variables? Okay, and we then move on to, remember, we've got to look at the interval. So look at the restrictions. They may be obvious, or you may have to really think about what the restriction on the domain is. Sometimes it's explicit and sometimes it's implied. Okay, so you have to be aware of what's going on. Then work out whether it's the max or the min, and then express your answer once you've calculated that. And often there's some assumptions and the effects of the assumptions. So they're your general rules of thumb and ways of going about it. So I hope to model what I've just suggested above with an example. And we have an open box. It has a rectangular base, and we're constructing it by getting a rectangular piece of cardboard. Now that initial cardboard has these dimensions, and you might have seen a scenario before. We're going to cut a little square from each corner, and the square is the same size, so there's going to be 4 little squares cut, and then we fold up or bend up the sides. Alright, now what we have to do is find the size of the corner square that will produce a box having the largest possible volume. Perhaps some of you, depending on what you did in younger years, might have done this with trial and error. Alright, or guess, check and improve. And you may have used a spreadsheet to help you speed the calculations up. Now we're going to do, with more complicated situations, we need better tools than just guess, check and improve or trial and error, and optimization is that tool. So here's that diagram. You can see that there's your rectangular piece of cardboard, and these here are the little squares. They get cut out and removed, so they're not there. And then you can see that these dotted lines represent the sides of the box as we fold them up or bend them up. So we need to relate volume and x. Alright, so it's volume versus x. Now in general we have a rectangular prism, so in general we have length by width by height. Now that is not going to wash in this problem just like that, so we have to adapt that idea. Alright, so the length you can see is going to be, it was 21. It was 21 for the actual piece of cardboard, but of course we're taking off little squares of side x, and so you can see, like for example up the top where I'm writing, that it's 21 minus x on one side and minus x on the other, so the length is 21 minus 2x. The width is 16 minus 2x, and the height, once you fold that up, the height is x. So we have a cubic polynomial. Expanding that out, we get that. So that's our polynomial for v. It's v versus x. So we've started work well and truly now. Now at this point it'd be very handy to look at restrictions for the domain, and we're talking about restrictions on x, which is the independent variable. So x of course has to be greater than 0. But what about the top end? Well, we look at the shorter side here, because it's going to, as x gets bigger and bigger, it's the short side, or the width, is the one that's going to give up first, if that makes sense. So what happens is that we can't have the width equal to 0. It'll be equal to 0 before the length, because the width is only 16 minus 2x. So basically we look at when 2x equals 16, x equals 8. So, whoops, that's an 8, sorry. And what we must make sure that x is less than 8. So, let's write that as a proper inequality. 0 is less than x, which is less than 8. Oh dear, so that should have said 8 there. Alright. Some people might argue that it's 0 less than or equal, 0 less than or equal to 8. But I would argue that for us to have a box, we would need, if it's not going to just remain as a piece of flat cardboard, we would need to make x bigger than 0. Some people would say it includes 0. I'm not going to say that. However, we want a box. What I've done now is take the derivative, so we'll call that v dash of x if the original is called v of x. And we know we need to look at maxima and minima in such problems. So factorize that now, and we need to look at the stationary points. Is when your derivative is equal to 0. So let's set it equal to 0. 0 equals 4 outside of 3x take 28 times x minus 3. And divide both sides by 4, we still get 0 equals 3x take 28 x take 3. Null factor law to solve that, so x equals 3, or x equals 9 1/3. Now this is where you need to be thinking. We need to consider these two solutions here, plus the restrictions on the domain that we had to come up with ourselves, which are up there in green. So x is between 0 and 8 exclusive. Now straight away this solution is mathematically valid, but it's not valid for this problem because it's bigger than 8. We can't have a square that big, there'll be no width. So that's not valid for this problem. Even though the maths is okay, it's not valid. So it's out of, we've got to set x equal to 3. And if we look at the two ends of the domain here, 0 and 8, we need to set x equal to 0 and x equal to 8 and test the values there, because we want to maximize the volume. If you go back up here, the largest possible volume. So we want to maximize that. Also we need to double check that that's a stationary point. Is it a maximum? and we can do that by checking just either side. As we've seen previously, you take values either side of 3, so you might try 2.9 and 3.1, and you'll find that it works as a maximum because you have a positive value for the derivative, which is a positive gradient, stationary point, and then afterwards it has a negative gradient. To save time, you need to calculate v of 3 in the original function, not the derivative, in the original function, v of 0 and v of 8, and you'll find that v of 3 comes up with the highest value for the volume. Now, you do need to check the endpoints as well. Okay, we've only got one turning point or one stationary point, and if it's a maximum, all we need to do is just check the endpoints, because that can be what's called a local maximum, and it might start to rise up on the ends. So we do need to check just in case it's what's called a local maximum, but it's not a local maximum, it's a global, it's a maximum across the whole domain. So across this domain it's a global maximum, so it's the highest point. Okay, but you do need to check those endpoints just to be sure. And so the volume, the Vmax, the volume max is 450 units centimeters cubed, so 450 centimeters cubed. Now always check with your graphics calculator and use the analyze graph max, and you'll find that it's confirmed. You may even want to graph that first so you sort of know what you're expecting there. Okay, and that's 1, 2, 3, 4, 5, 6, 7, 8. See how we restricted the domain, which excludes that fella there. Okay, and perhaps you'd have to see, is that a maximum anyway? Perhaps it's a minimum, because if you let the graph go, does that dive underneath